Okay, so we have our last talk of the session from Professor Jiapeng Zhang from the University of Southern California. And Jiapeng is an assistant professor of the University of Southern California. His research primarily focuses on complexity theory and cryptography. He has received several awards, including the Stock Best Paper Award and the TCC Best Young Researcher Paper Award and an NSF Career Award. Okay, let's welcome Jiapeng.
Okay. Thank you for the introduction. Okay, so. Okay, sure. Yeah.
So, Jiapeng, you want to maybe talk something first? Because there's something issue with the technical things.
Okay.
Yeah, maybe, is there anything you can share without the slides?
Okay, so start without slides. Okay, sure.
Yeah,
okay, okay, so I will just talk without slides. Today I will talk about fully homomorphic encryption, and also how to verify fully homomorphic encryption. Okay, so here is the thing, as the previous two speakers also mentioned, that in many cases, so people want privacy, right? So they hope their transaction and the balance amount to keep it private. And in beyond of that, so in many cases we want to keep privacy. So for example, if we want to outsource some computation, for example, if you want to, if you have something you want to run a large language model from OpenAI's models, for example, so you can. Usually, people just send their data to the okay, cool. Yeah, we can start. Okay, so today I will talk about efficient verifiable fully homomorphic encryption with Ring-R1CS. Okay, so okay, so this is a joint work with several persons, with Ming Huang and Xinyu Mao from University of Southern California. They are my students, and also joint work with Baiyu Li from Google, and also Xiao Chen from Site AI. So today I will go through 4 parts. At first, I will going to introduce what is fully homomorphic encryption, which is one of the most amazing tool developed in cryptography community in past 10 years. And also then I will talk about the snarks, and then how could we prove for FHE computation. And so, yeah. Okay, so let's start. Okay, so let's start with fully homomorphic encryption. Okay, so what is the idea of homomorphic and what is the purpose of homomorphic encryption? So imagine that you want to compute something and you have the data, but you don't have the computational power, for example. So such as you have to use data from AWS. So, but you want to keep your data private. Some of the data could be very sensitive. So, but you don't want to share this data to Amazon, but you have to use the Amazon's computational power to finish the computation. So what should we do? This is outsourced computation, and so this is one example. And the other example is that you want to something you want to such as the blockchain, right? So all of the transactions, you want to hide the information of the transactions. So the previous lectures discussed the several solutions, and here so there's another solution which is called fully homomorphic encryption. Okay, so what is the process of fully homomorphic encryption? Here's the idea. So in the beginning, so we have data. So it includes all kinds of data, probably biological data and also financial data or whatever, any kind of data. And we want somebody else, the server or blockchain or whatever, AWS, to finish the computation. So the process is that we first encrypt our data. And so we submit the encrypted data to the server. And then the server could do the computation for me. So they do the server do the computation in the black box. So, but even the server did the whole computation, but the server knows nothing about this data. So for example, I want to compute 3 plus 5. Then I encrypt 3 and encrypt 5, submit to the server. But the server doesn't know what is 3 and what is 5, and just to do some mysterious computation and then return me a ciphertext. This ciphertext looks random to the person who does not have the private key. But however, for the user who has the private key that decrypted it will be surprisingly the output is 8. So this is for the homomorphic encryption. Okay, so let me quickly tell you, high level tell you the syntax of for the homomorphic encryption. So it includes several parts. So it includes the generation part. So basically the generation several keys. One is the public key. Public key is given by everybody, and the secret key. The secret key, the user has the secret key, and there's also a key called the evaluation key. Okay, 3 keys. And the encryption is that for anybody who has the public key can encrypt the message. And after this, and also the evaluation, so for any people who have the evaluation key and have one function, f. Yeah, function f could be arbitrary function, such as multiplication, a large language model, or whatever. So just a function, polynomial time algorithm. And also the evaluation key takes also some inputs of the C1 up to CL. These are the encrypted data. So this data are subtext, encrypted data. And also the lastly, who has the secret key can decrypt the subtext. So this is the whole process. Okay, so usually we hope that why we call it homomorphic encryption. So at first there are several names here. So the first one is called 40. So what does 40 mean? The 40 means this F could be arbitrary polynomial time circuit or polynomial time algorithm, you can imagine it. So 40 means any polynomial time algorithm. In beyond the addition, multiplication, it could be very, very general. And also, so we hope the homomorphic means we can do the calculation. And the 40 homomorphic encryption means that we can do, for every function, we can do this computation. So that is, originally, so people have some input, M1 up to ML. So we first encrypt them and submit it to someone else. Then someone else do the evaluation. Then the evaluation, then send the evaluation result to the user. And the user secret key can get the original output of FM1 of the FML. And also, so we also hope this is secure. So what does it mean? This secure is that for any ciphertext, meaning encrypted message, encrypted M, so then any polynomial time algorithm cannot learn any information from it unless this person has the private key. So without the private key, so all of the ciphertext doesn't look at random string. So this is a fully homomorphic encryption. So so it has many application scenarios. For example, so it can be applied to cloud computation. It can be applied to blockchain, and it can also so in many cases. So for example, it can also apply to MPC. So for example, probably Elon Musk and Jeff Bezos, they want to compare who is richer. So of course they don't want to tell the other people how much they exactly have. So they can run MPC. They can run this MPC and also this homomorphic encryption. So basically, each of them just encrypted their data, encrypted their balance. And then the F is just a function to be greater than, who is greater. So the output, they only need to decrypt the output. They can know who is the richer. Okay, so you have many application scenario. Okay, so it looks good so far. So it hides all of the privacy, I would say computationally perfect. So nothing was revealed unless they have the secret key. So basically you just need the secret key to hide everything, hide all of the computation. Okay, so it looks good so far. However, there is still an issue, which is how could you promise the server? Also, I just use the server, for example, so to return the correct answer. So probably I can just return, probably if I submit some computation request to AWS, for example, so then I encrypt my data and ask AWS to compute something. But it's possible that the AWS just want to be lazy, just return me a random answer, right? So how could we know they are correct? So in blockchain, so verification is a very important thing, how to verify the computation and verify it. So verification is also an important thing. So in here, the FHE only promises the security, privacy, but does not promise the integrity. So people can cheat during the computation. So so in order to address that, So actually, there is another very fancy tool, and also mentioned by previous speakers, so which is called zero knowledge proofs. In here, so zero knowledge proofs contain several parts. One is ZK SNARK. It's a ZK and a succinct non-interactive argument argument of knowledge. So there are several concepts. So, but in here, so we do not need zero knowledge. So why we do not need zero knowledge? Because the FHE is already secure enough. FHE already hide all of the information. So we want a succinct non-interactive argument. So basically, we want to, whenever the server is going to generate to run the computation, so at the same time, the server can generate a proof. The proof is going to prove the computation is valid. It is a correct computation, and the verifier can just simply verify it, which is called a succinct. Succinct because the verification is very shorter than the proof. Okay, so this is how could we ensure the server executes the FHE scheme honestly. Okay, so let me use this picture again to explain the whole process. The whole process is that we first encrypt the data. So the user encrypts the data and sends it to the server. So the server run homomorphic encryption to do computation on this data. And then they just, at the same time, it uses the SNARK to generate a proof. And in addition of sending the ciphertext to the server, it also sends a proof. The proof is the proof is a proof of the valid computation. And then finally, the user can decrypt the information. The proof. The user can decrypt the ciphertext to get the answer, and also can validate the proof to address whether the computation is correct. So at this moment, then the user can be convinced the computation is a correct output. Okay. So this is the SNARK. So SNARK. So I'm also going to quickly introduce you what is SNARK. So the SNARK. So this is the syntax of SNARK. So you generate some random strings, and there is a prover in the prover is going to prove something, and so take it can prove to generate a proof and verify it. Given this proof can generate the proof, so it can verify whether the proof is a correct proof or not. Okay, so then what is So what we want the SNARK to be what are the properties we want from the SNARK? The SNARK is that so the proof. So one thing is the completeness. So for every circuit C, so meaning the FHE computation and any input X and output Y. So whenever the Cx equal to Y, meaning the server has run the computation honestly, so then the verifier will accept the computation, the proof with high probability. Otherwise, if the server is cheating, okay. So the other side is what is called soundness. The soundness is that whenever the algorithm was cheating, and so then the proof generated by algorithm cannot be verified by, won't be accepted by the verifier. So this is the SNARK. And one of the very important things is that the verification time must be very, very shorter than verification, not much faster than rerun the whole computation. That's why we call it SNARK, because we can save the verification time. Okay, so we have two tools, and we can combine them together. So here's the naive approach. So the simple approach to address the integrity of the FHE computation. So we can start with any FHE computation, right? So and what we can do is just we can convert the evaluation process, the homomorphic evaluation process, into an algorithmic circuit. So after converting to a circuit, we generate a SNARK proof for the circuit. And so then lastly, we can just decrypt the ciphertext and check whether the SNARK proof is correct or not. So the whole pipeline sounds very convenient and very powerful and a very complete solution of everything. But however, there's one issue here is the conversion. So if you want to convert the evaluation process to the arithmetic circuit is very, very inefficient. So this conversion process is very, very inefficient. So for the FHE, we know FHE is the performance of FHE is already not good, not fast enough. And if you also want to generate the proof, if you use this naive approach, so the running time of the snark is at least the square of the running time of the FHE. So this is very, very inefficient. So there are several reasons. So why these are not inefficient? Okay, so the last part could be a little bit of technique. So one of the reasons is that the FHE schemes use the ring structures. If you learned abstract algebra before, it's that the FHE based on some of FHE based on ring IWE or whatever structures. So they do computation on rings. However, the arithmetic circuits are based on fields. So there's a gap between field and rings. On the other hand, so the FHE scheme usually has some complicated operations such as modular switching and key switching. So these complicated challenges are very, very hard for generating snark proofs because their polynomial degree is very high. So we cannot use the low degree polynomial to verify the switching to generate a proof for the modular switching and key switching. Okay, so how could we address these two issues? So this is our current ongoing research project, and we are currently writing a paper to address these two issues. So the first one is how could we fill the gap between rings and the field? So if we check the snarks, so why we use why we have to use field instead of using only rings? One of the main reasons is the Schwarz-Zippel lemma. So this is one of the fundamental mathematical lemma in snarks or ZK snarks or whatever. So basically the proof, so probably you might learn it from high school or whatever. So the simple version of this Schwarz-Zippel lemma could be written in this way: is that any degree d polynomial or a field. So for any degree t, if the polynomial has degree d, then it has only most d roots in this field. So okay, so this is one of the fundamental tool, and so because in the snarks, we hope everything to be low degree polynomials. So okay, sorry. Okay, sorry. Oops. Okay, so this Schwarz-Zippel lemma, why we cannot apply to rings? One of the main reasons is that this lemma does not hold for general rings. Whenever this lemma does not hold, what does it mean? Then the soundness of the snark won't be correct with high probability. We cannot keep the soundness in the snark proof. So that means if this lemma is failed, then we can the verifier, the proofer can generate fake proofs, and also the verifier will accept these fake proofs. So therefore there is no soundness. Okay, so but this is not true for general fields rings, but fortunately it is also true for nice rings. And we have some generalized Schwarz-Zippel lemma, and this is a paper 6 years ago. Okay, so for some any question? Nice rings, this is true. Okay, okay. So and also now we could think about how to design snark-friendly FHE. So in order to design snark-friendly FHE, so we need to rewrite the FHE scheme from the existing FHE schemes, because in the existing FHE schemes nobody considered the proofs before. So people just focus on the efficiency of snark of FHE. Okay, so we need rewrite the existing FHE to make all of this complicated operations such as key switching and modular switching can be represented by low degree polynomials. And also we need FHE to be run in the nice rings. And also we need intermediate representation between FHE and SNARKs. How could we convert the FHE computation into this nice ring? So we need some intermediate representations. Okay, so then what is our solution is that, so we started from FHE scheme called FHEW. And so this is the FHE scheme proposed by Daniele Miciano and Leo Lucas. And so actually, so so this FHE scheme also inspired another FHE scheme, which is called TFHE, which is used by Zama. Okay, so FHE scheme, we choose FHE scheme for some specific reasons, because FHE scheme W have some advantage of being having nice rings and also nice connection to R1CS. Nice connection to SNARKs. Okay, so the second step is that we want to choose nice rings. So we choose some nice rings based on the power of 2s. Okay, so there are some reasons, very technical reasons, but of course I don't have time to explain it today. And then the last part is that we introduce the Ring-R1CS as intermediate representations. So R1CS is a very important tool in SNARKs, in the existing SNARKs, and the R1CS was based on ring fields. So this is how so in order to make the FHE SNARK friendly, so we really need to fill the gap between rings and the fields. So therefore we introduced a notion called Ring-R1CS. And so the high-level idea is just to combine, to use the generalized Schwarz-Zippo lemma. Okay, so after all of this improvement, so in the theoretically, we can show that this generates the proof generation time after this optimization. So the proof generation time is almost linear as the FHE computation time itself. So meaning, so the overhead of proof generation won't be very horrible. So it still takes some time. Okay, so yeah, that's it. Thank you.
Thanks, Jiapeng, for the nice talk. Any questions? Quick questions? Okay. Now, in the interest of time, let me maybe. Oh, yeah, actually, we have a question. Yeah.
Thank you for your presentation. Because I'm not an expert, but I'm really interested in the abstract algebra because I've learned it in high school. So the question is, how can you generalize the Schwarz,
Schwarz-Zippo.
Yeah. Because in fields we have an inverse of the multiplication, right? So that's the key in proving the lemma. So how can you generalize?
Okay, so there's a previous work. So in 2018. So basically, so for the rings, even they do not have some inverse. So the rings, you just compute the roots of polynomials. So there's no inversion here actually. So we just need to, because the inversion promise you give the upper bound of the number of the roots. But in here, so the number of roots itself does not have any inversion, right? So they introduce something called exceptional set, and so they say if the anyway, so they have some nice property here. So yeah, you can check out the paper.
Yeah. Okay. In the interest of time, let's thank Jiapeng again for the interesting talk. Yeah. Next, Prof. Wen Yonggang will give the speakers our token appreciation. Yes. Joseph, please, and Prof.
Joseph.
个这些。
Hi everyone, we'll be having a 10-minute tea break. So all the general attendees can go to the back and have some tea, and all the all the VIPs and the guest lecturers on the left. We'll be back here by 11:10.